Let's dive now a little more deeply into the state function known as enthalpy, which we saw in the last video, the change in which is equal to Q, the heat evolved or absorbed during a constant pressure process. So we demonstrated in the last video that the heat of a chemical reaction or any other process at constant pressure is equal to the change in enthalpy of the chemical reaction system. The enthalpy change for a process tells you whether or not it absorbs or releases heat, and as we mentioned at the end of the last video, that's useful information. But now heat and enthalpy change are extensive quantities because a higher mass, for example, or more reaction events is going to cause a larger absorption or evolution of heat. To get an intensive measure of enthalpy that is a little more transferable to different contexts, different scales of reaction, for example, we can divide by the moles of substance involved in a chemical reaction to get an intensive measure called molar enthalpy. Throughout this video and others, I'm going to use a subscript M to denote molar quantities, per mole quantities. Now, enthalpy is a state function because it's just a composition of other state functions, U, P, and V. And it's worth noting as well that molar enthalpy has units of typically something like kilojoules or joules per mole. It's an energy. The units of enthalpy are the units of energy. U is, of course, internal energy, and P times V is also a unit of energy. Remember, P delta V is a measure of work. Work and energy are equivalent, and so P times V has units of energy as well. Molar enthalpy has units of energy per mole. It's important to develop an intuition for the sign of enthalpy. There are two possible signs for enthalpy changes, negative and positive. Processes that involve a decrease in enthalpy within the system, which cause a release of heat to the surroundings at constant pressure, are called exothermic. And here's a diagram that shows you a hypothetical exothermic process. The change in enthalpy of the system is less than 0, and from the system's perspective, Q is less than 0. This will cause the surroundings to increase in temperature, since the system is transferring heat to the surroundings, and we'll measure this as, for example, an increase in the temperature of the surroundings relative to its starting point. Processes involving an increase in enthalpy within the system, which cause an absorption of heat into the system at constant pressure, are called endothermic. And in this case, since the system is absorbing heat from the surroundings, delta H is greater than 0, Q is greater than 0, and we would observe a decrease in the temperature of the surroundings relative to their starting point, since heat is being transferred from the surroundings into the system. One way, hypothetically, we could determine reaction enthalpy is simply to run the reaction and measure Q to determine delta H directly, and then use stoichiometry to get an intensive quantity in, say, kilojoules per mole. A more systematic and more efficient way to do this is to think about the standard enthalpy change of reaction so that the conditions don't have to follow the delta H value around wherever it goes. Delta H depends on the temperature and the pressure at which the process is occurring. And so this idea of defining a standard is important so that we can report delta H values under standard, well-defined conditions. And the standard enthalpy change of reaction is defined as the change in enthalpy for 1 mole of reaction events at the standard pressure of 1 bar and 1 mole of reaction events. And so A moles of A and B moles of B in a general reaction like this, where A and B might be non-1, might not be equal to unity, the standard enthalpy change involves A moles of A and B moles of B forming C moles of C and D moles of D. And keep in mind how we defined a reaction event. That corresponds to a single reaction event. A molecules of A reacting and little b molecules of B reacting represents one reaction event. The nice thing about enthalpy is the details of how the reaction takes place are irrelevant as long as we understand what the initial and final states are. Enthalpy is independent of the specific, for example, reaction mechanism or the exact path followed by the reactants to reach the products. Hence, we could send the reactants to Mars, for example, and bring them back before converting them to products, and the molar enthalpy change of reaction would still be the same as if we just ran the reaction here on Earth. So we don't need to be too concerned about what happens in the middle of a reaction as long as we take care to define the initial and final states carefully. Any way we run the reaction, the standard molar enthalpy change of reaction will be the same, as long as the initial and final states are the same. This should bring back this analogy of the routes traveled between Atlanta and Athens. For certain changes in certain functions that we found were state functions, it didn't matter the route we traveled. The change in temperature, for example, between Atlanta and Athens did not depend on the route we traveled. Enthalpy works the same way, so we think of the reactants as kind of living in Atlanta. There's an H, or an enthalpy, for the initial state of being in Atlanta, and there is an enthalpy for the final state of being in Athens. The enthalpy change in going from Atlanta to Athens doesn't depend on the path traveled, only on the difference between H sub Ath and H sub ATL. So while we can measure the standard enthalpy change of reaction simply by running the reaction in the open air and measuring Q, this is actually quite a bit of a pain, because if we had to do this for every reaction of interest, it would have to be done anew for every chemical reaction that we would want to study, right? So that's a pain. However, we can use Hess's law to our advantage here. Hess's law, in a slightly restated form using enthalpy, which is a state function, says that the net enthalpy change for any sum of reactions that adds up to our reaction of interest is equal to the enthalpy change for that reaction of interest. In mathematical form, if our reaction of interest was converting, say, state 1 to state 3, or reactants 1 to reactants 3, and we knew the delta H's for converting 1 to 2 and 2 to 3, we simply add up these two enthalpy changes to get what I'm calling here the net enthalpy change. That net enthalpy change is equal to the enthalpy change for the conversion of 1 to 3. The reactions on the right-hand side sum to conversion of 1 to 3, and the delta H's also sum, and that's a consequence of H being a state function.